All right, so we're going to pick up where we left off yesterday in section 7.6. And we're solving equations that pretty much every time it boils down to turning into either a quadratic that you can factor or one that you have to use the quadratic formula. So, regardless of which type it is, Kaya, what do you always want to get your equation equal to when you're trying to solve it? Yep, always want to get it equal to 0. And the best thing to do is to put the squared term on the right in this problem. Now, I want the squared term to be positive. So at first you might think, well, putting it on the right is not going to make it positive. But it's going to be positive in the next step. So let's write 0, negative 2 sine squared x minus sine x plus 1. Now, is that a quadratic pattern? No, something wrong. What's wrong with it? Because it's got the 3 terms. The last one is just a number. One exponent is double the other. But what's wrong? Yeah? It's okay that that's a negative. We're not worried about that negative because that's going to go away in the next step. But there's something else wrong with that term. Yep.
Terms are not the same.
Right. You can't mix sines and cosines in the same problem. It's like mixing variables. So we use this identity a lot. And we're going to use it again. So we're going to put negative 2. Just leave it because you're going to substitute something in. And what can I plug in for cosine squared?
1 minus sine squared.
Yep. That's nothing new. You did that yesterday. And now, Jacob, what do I have to do with that negative 2? Yes, we're going to distribute it out and then just combine like terms. So we'll do all that at once. Nikira, what's negative 2 times 1? Plus 1. Negative 1. Negative 1 minus times a minus. This is why I did it this way. Minus times a minus gets rid of that minus, and now it's a plus. So 2 sine squared x minus sine x. Okay, now, is that a quadratic pattern at this point?
Yeah.
Yes, it is. So what sometimes I do temporarily is I just write it like this. And if you can figure out how to factor that, then that one will factor the same way. But I'm not sure if it's factorable. Let's give it a shot. So what would your first term have to be in each parenthesis? You'd need a... Yep. Yep, and next, your signs have to be a plus and a minus. Again, I don't know if this is going to work. We may have to use quadratic. So a plus and a minus, and 2 numbers that multiply to give you 1 are 1 and 1. I think we're good. 2x times x is 2x squared. 2x times negative 1 is negative 2x. 1 times x is positive x. Negative 2 plus 1 is negative 1. So yeah, we factored it. So we're not going to have to use quadratic formula. Now, remember, we just did this little trick to make it look less confusing to factor. But really, all your x's should say what? Sine x. Okay, so this little step, again, this is temporary. If you want to do that step, but the real factoring should be this. 2 sine x plus 1 and sine x minus 1. Now you're at the step that all the homework problems were. We have 2 factors equal to 0. Chris, what do I do with each factor? Yeah, set each factor equal to 0.
Yeah.
Find the 0 of each factor. So if you set the first factor equal to 0, you'd have to get the 1 on the other side and the 2. Sam, how would you get the 1 on the other side?
Subtract.
Yep. And how would you get the 2 on the other side?
Divide.
Yep. So we got sine x equals a half. And Brianna, on this one, it would be sine x equals 1. Let's do this one first, because anytime it's a 1, a negative 1, or a 0, all you got to do is look at the picture. We'll do this one in degrees and we'll do radians to practice both. Where do you hit 1 on that graph? Yep. 90 degrees. So x equals 90 degrees, or what is that in radians?
Divided by 2.
Yep. Okay, those aren't different answers. They're just two ways of saying the same thing. Whenever it's a 1, a negative 1, or a 0, you don't have to do the ASTC thing. Just look at the picture. I can tell that it only hits 1 time per cycle. Right, now let's do this one. Okay, how am I going to get rid of sine to get x by itself? Yep. So we're going to do the inverse sine, negative a half. And before I even type it in, let's just think. I'm looking for where sine is a negative number. That's going to happen here and here. So the calculator is not going to give me a referencing because there are no quadrant 1 answers in this problem. So we're going to have to work backwards to figure out that referencing. So second inverse sine of a half, negative a half is negative 30. Now, what can you add to that to make it a positive number? Because if they ask for answers between 0 and 360, you don't want to put that down. Yep.
80 or 90.
So think about like on the circle. What's this coordinate?
90.
90. And you went like that. What's this coordinate? Doing what?
60 plus.
360 plus 90. So he added 360 and it came out exactly the same.
Oh, so add 360.
So add 360. You add 360, that will come out exactly the same. So that's 330 degrees. What quadrant is 330 in? Yes. There's your fourth quadrant answer. Now, we need the third quadrant answer. What's the formula for quadrant 3?
270 minus the referencing.
No. We don't, for these formulas, we never use the 270. It's either 360 or 180 plus the reference angle. So all you need to do to get the other answer is figure out that. Well, you've got an answer in quadrant 4. Quadrant 4 is 360 minus the reference angle. But you already know the answer in quadrant 4. It's 330. So, I mean, without really spending too much time on that, does anyone think they can tell me what the reference angle is?
30.
It's 30. Yeah. The reference angle is 30. So, your reference angle is 30. Fill that in right there, and that's your answer in quadrant. Right, so x equals 210. Now, if they wanted those in radians, that would be the last step. If they wanted degrees, we're done. Okay. Radians, Let's see. So take 330 times pi, divide by 180, cross out the zeros, and 33 and 18 are both divisible by 3. 11 and 6. So 11 pi over 6. Do the same thing again for 210. 210 times pi, divide by 180, cross off your zeros, and those are both divisible by 3. So that's 7 pi over 6. So there's every answer for this problem, every way I could ask you for it on the test. Degrees and radians. From now on, I might just stick with degrees. Unless people want to keep seeing the radians, we can practice another radian. Okay. Any questions on that one? Okay, so let's try this one. Example 3. Now, I'm just going to note real quick what they're saying here. For whatever reason, they only want answers between negative 90 and 90. We're going to do it in degrees. So, this could be a quadratic type pattern. One exponent is double the other. It's not a 1 and a 2, it's a 2 and a 4. Okay, but it still could be a quadratic type pattern, which means it could be factorable. But if we're going to try to factor it, what do we want to get it equal to first? 0. So you can do it a couple ways. I'm going to put everything on the left, because every time you factor, you always want the term with the highest exponent positive. Whether that highest exponent is a 2 or a 4, keep it positive. Right? So let's put everything on the left. We got that. Minus secant squared, minus 1. Now, we've got everything on the left. But what's the problem with this? We're trying to factor them. Same problem we've seen before. Yeah.
Those aren't the same.
They're not the same function. You have a tangent and you have a secant. Well, we've been using the identity sine squared plus cosine squared equals 1. It's the same group, but it's not that one. You always substitute for the one that's squared. So we're going to substitute for what's in parentheses. But what's the identity that's a Pythagorean identity and has secant squared in it? Jared?
1 plus tangent squared is equal to secant squared.
Yep. That's one you should definitely have on your reference sheet. 1 plus tangent squared equals secant squared. So let's make that substitution inside the parentheses. Now you're going to have some like terms. You could do this all at once, but let's do it in 2 steps. Secant squared is 1 plus tan squared. Everything else I copied down, except for secant squared, I changed it. Caleb, what do I have to do with this negative?
Wow. Just switch it.
What do you mean? What do you mean switch it?
Distribute it.
Distribute it. So whenever you do a Pythagorean substitution, there's usually a number to distribute. When I asked Jacob about it, it might have been a 2. I don't remember what it was. But usually there's something to distribute. So now we've got that. That's just going to stay there. Minus 1, minus 1, which is how much? Minus 2. So minus 2 and minus tan squared x. Okay. Is that a quadratic kind of pattern? Yes, it is. There's 3 terms. The last one is a constant. The functions are the same. That exponent is double that one, which means it's either going to factor or we can use quadratic formula. Let's try to factor it. Just for, again, kind of a visual trick, let's temporarily write it like this. And if you can factor what I just wrote, it's exactly the same as factoring what's up above. What would have to be your first term in each parenthesis? So when you multiply them together, you get 3x to the fourth.
Squared.
X squared would be one of them. And? Yep. Now remember, that's really a tangent where the x is, but we'll change it back after. We got a negative middle and a negative constant. So what should my signs be? One positive, one negative. We might have to switch that order. I'm not sure yet. And now two numbers that multiply to give me 2.
1 and 2.
1 and 2. I'm going to try it in that order and see what happens. 3x squared times negative 1. There we go. 2 times x squared is negative 3x squared plus 2x squared, what we want. What is negative 3x squared plus 2x squared?
Negative 1.
Yeah. That's what you want. Negative 1x squared. So this is factorable, which means you're not going to use quadratic formula. Okay, this step right here, that's temporary. Only if it helps you to factor it. Now we need to really write how it factored. All the x's should really be tan x's. So we've got 3 tan squared x plus 2 tan squared x minus 1. I just changed the x's back to tangents. And now from here, it's like your problem in the homework. What are we going to do with each one of those factors?
0.
Set them to 0. 3 tan squared x plus 2 equals 0. Remember, think of this tan squared x as like a block. You've got to get the block by itself first. Then you can deal with the exponent. So, what would be your first step to get tan squared x alone? Subtract 2. And then? Divide by 3. Now, we're trying to get x by itself. If it's more helpful for you to think of it this way, that's the same notation. Most people don't write it that way, but you can. That is how you have to write it on a calculator. I usually write it the first way. So, we can't do inverse tangent yet because we still have to deal with that exponent of 2. So how do we undo squaring tangent and get it back to just tangent? Yeah. Take the square root. Square root and square cancel. And now, how would you, so you got it from tangent squared down to tangent, how would you get it from tangent to just x? How would you get rid of tangent? Yeah.
Inverse tangent.
You would take inverse tangent, but how come I can stop at this step? I don't need to keep going for this side. What happened there?
Because you can just plug it into the calculator and see when it equals the square root of negative thirds.
You can try. Yeah? That's the square root of a negative number. That's imaginary. So from this part, there's no solution. You can't take the square root of a negative number. Had this factored as like a minus 2 instead of a plus 2, then you would have been good. But that's not how I factored. So we don't have to worry about that whole part. Okay, so now let's just worry about this part. Tangent squared x minus 1 equals 0. We're going to add the 1, and this time you're adding it. So you are going to end up with a positive number on the right. Versus over here, you subtracted it. So now you can take the square root of both sides, and that works. Square root, square root. That cancels. Now, be careful here. What's the square root of 1?
1.
What else?
Oh,
Because if you forget this, you lost half your answers.
negative.
Right. Square roots always have 2 answers. So this part kind of breaks itself up into 2 problems. Tangent of x equals 1. Tangent of x equals negative 1. And now you're at the step in the homework where you take inverse tangent on both sides. So, let's see what happens. So, let's go second inverse tangent of 1. You're just believing it's 45. So we got that. Okay. I'm looking for where tangent is a positive number. I got an answer here. Where else is tangent positive? Yep.
Third.
That's 180 plus 45, which is how much? Yeah. It's 225. They don't want it. They said justify the answers from negative 90 to 90. So for whatever reason, they don't want to know the 225. You don't have to write it down. It's good that you know how to find it in case they did want it, but they don't. Any question on that? And now, let's do this one. Second inverse tangent of negative 1 is negative 45. Now, is negative 45 a number that they would want? Yeah, they want negative 90 to 90. So don't add 360 to it. Negative 45 is the same as 315, but they don't want you to write it that way. For whatever reason, they just want you to leave it negative this time. And now, you don't have to worry about the second answer here for the same reason you didn't here. You can find it if you want. But like this one, we found it and it was 225. When you find this one, it's not going to be between negative 90 and 90. So you don't have to worry about it. If you actually went through and did it, the second answer would be in quadrant 2. That's 180 minus 45. That's 135. That's not what they want. They want negative 90 to 90.
So it would be in quadrant. Oh.
Because tangent would be negative here and here.
Oh.
Negative 45 is that one, right? Negative 45 is the same as 315. So this is a fourth quadrant angle. And the second quadrant angle would be 135. But they don't want it. Okay. Any question on that one? It's a little bit tricky because you just had to remember here you can't take the square root of a negative. Right? But then the other part worked out pretty nice. All right, so we have that one and that one. 2 left. All right, if you look at this one, it looks different. Right? How many terms do you see in that problem? Yeah, there's 4. Anytime you see 4 terms, it's not a quadratic pattern at all. So what that means is it's going to have to be easier because when it's not quadratic, you can't use quadratic formula. So how do you think this problem is going to have to be solved if you can't use quadratic formula? It's going to have to what?
Factor.
It's going to have to factor. Yeah, it has to. Because it's not a quadratic pattern, and it is going to factor in a special way called factor by grouping. 1, 2, 3, 4. Factor by grouping is where you factor out what the first two terms have in common, and then factor out what the second two have in common, and hope that something nice happens. If I tell you to factor by grouping, something nice will happen. So look at the first two. What do the first two terms have in common?
Cosine of x.
Cosine of x. So that's the first step. Factor that out. If you factor out cosine x from the first term, what's left?
2 cotangent x.
2 cotangent x. And what if you factor cosine x out of the second term? What's left?
6 cotangent x.
Second term.
Oh. 3.
So with factor by grouping, the hope is that you get 2 cotangent x minus 3 again. If you don't, then you can't do factor by grouping. So let's see what happens. What can you factor out of terms 3 and 4? What do they have in common? Yeah, 3. If you factor a 3 out of a 6, what does that leave you with? No. If you factor a 2 out of a 6, that would leave you with 3. What if you factor 3 out of 6? 2. 2 cotangent x. And what if you factor a 3 out of negative 9?
3.
Negative 3.
Yeah.
So now, look what happened. 2 cotangent x minus 3, 2 cotangent x minus 3. So you started with 4 terms. Now you have 2 terms. 2 big terms. Now, factor out what you can again. The 2 things that I just underlined, what do they both have in common?
Cotangent x.
Yep, so do it again. 2 cotangent x minus 3. If you take that away from the first one that's underlined, all you're left with is cosine. If you take that away from the second one that's underlined, what are you left with there? Yeah, just the plus 3. And that's equal to 0. Now from here, it's just like the homework. You have 2 factors equal to 0. So what are we going to do with each factor? Yeah, make them equal to 0. So it's the same thing. I'm going to do the one on the right first, and I'll show you what happens with that. If you set the one on the right equal to 0, it would be cosine x equals, what would go on this side of the equal sign? Negative 3. Now, think about the graph of cosine. When you draw cosine, it looks like this. Where does it hit negative 3?
Never.
It doesn't. The highest is 1, the lowest is negative 1. So there is no solution from this part. So you don't have to worry about any answers there. If you're not sure, take the inverse cosine of negative 3 and you'll get an error. Okay, so now let's look at this one. Think of this cotangent. It's like a block. You got to get that block by itself first. How would we deal with the negative 3? Yep. You would add it. And how would you deal with the 2? Yeah. You divide it. Now we want to get x by itself. So how do you cancel out the cotangent function?
Inverse cotangent.
If you had a button for it on your calculator, you would want to use inverse cotangent. There is no button for that on the calculator.
It would be 1 over inverse tangent.
So you're thinking along the right idea. So we don't have a button for inverse cotangent, but what trig function is this connected to? It's similar to. Yeah? It's very similar to tangent. And if you know the cotangent, you automatically know the tangent as well. What's the connection between cotangent and tangent? If you have one and you want the other, you just do what with it? Yeah. Which is basically does what to it? It just flips it. So if I tell you the cotangent of 3 over 2, the cotangent is 3 over 2, then that means the tangent is 2 over 3. So that's a little trick I don't think we had seen in any problem yet. But you don't have an inverse cotangent button, but you do have an inverse tangent button, and now you're good. What quadrants would you be looking for answers in here? Give me one quadrant. First quadrant. And Brandon, what other quadrant? So you know how to read what this diagram tells you? So it tells you where the trig functions are positive. So we're looking for where tangent is positive. And Jared said quadrant 1 because they're all positive. What other quadrant does tangent come out positive? Which one? 3. So we're looking for answers in quadrants 1 and 3. The calculator is going to give you quadrant 1 right away, which is your reference angle, so that's good. Okay, so let's try it. Inverse tangent of 2/3. 33.69. Chris, what's my formula with my reference angle in the quadrant that Brandon just told us? So it's not, Nikira?
180 plus the reference.
Yeah, it's always 180 or 360. So this one is 180 plus your reference angle. So it's 213.69. Okay, so anytime you see a problem in the homework or on the test, if it's got 4 terms in it, it's going to have to factor by grouping. That's the only way to do it. So in a sense, it's actually easier when it has 4 terms because you don't have to worry about should I be using quadratic formula or is it going to factor? It's going to factor. It has to. Okay. And last one. So it says sine 2x equals sine x. Is this a quadratic type of problem? No. It's not a quadratic problem at all because it's, first of all, you've got the same trig function, but you don't have something squared and something to the first. Okay, so you don't have that. You also don't have a constant. Okay? If there's no constant, you don't have that third term to make it a quadratic pattern. There is no third term. It's only 2 terms. So the first thing we want to do is get it equal to what we always get it equal to. So Sam, what do we always want to get it equal to?
0.
And how would you get 0 on the right?
Sine.
Yep. So you get sine 2x minus sine x. Now, that 2 is a huge problem. You can't have a 2 there. Just like you need to have the sine and the sine match, you need to have the x and the x match. Right now, that's an x, that's a 2x. That's no good. So this part is okay, minus sine x. We need to fix sine 2x. So on Monday, we learned something you can plug in for that. what can you change sine 2x into? Yep.
1 plus cosine 2x.
No.
Close.
Not quite. Do you remember what group of identities these were called when you have a 2? When you have a 2 in front? Like we had the Pythagorean, we had... What group of identities is this? Yep. Double angle. That's a double angle identity. So what we need is the double angle identity for sine 2x. So what if... Yep, here.
2 sine x cosine x.
Yes. Now, you've gotten rid of that 2 in front of the x. You kind of messed up a little bit here, and now you've got a cosine mixed in with the sines, but that's okay, because it's only 2 terms. 1, 2. If it's 2 terms, it's always going to be easy to solve. Look at the 2 things I just underlined. What do they have, what do they have in common? So whenever they have the same thing in common, what do we do with it? Factor. So let's factor out the sine x. Jacob, if I factor out sine x from the first term, what's left?
2 cos x.
2 cosine x. And Eric, if we factor sine x out of the second term, what's left?
Nothing.
Well, you can't put 0 here, because then if you distributed that back out, you wouldn't get back what you started with. Right? You got to put a 1. Okay. Now, what do we do with each factor? Yep. No, you don't want to distribute it back out, because if you distribute sine back out, it's going to change it back to what you started with. So what do we do at that step? Yeah. You don't have to change any of your trig functions anymore. You're at the last step of the problem now. It's the same last step that we have to do in every problem, if it factors. This is always what you do after you finish factoring. Yep.
Set each factor to 0.
Yes. Set each factor equal to 0. Sine x equals 0. Cosine x equals a half. Let's see if we can just remember it from the graph. Where does the graph of sine hit 0?
Negative half?
Plus 1 divided by 2.
It's
Positive. Where does the graph of sine hit 0?
0.
0 and one other spot.
No. On the 80.
180. Yep. So 0 and 180. And now, where does cosine x equal a half? I feel like we've done this one a bunch of times somewhere. Wasn't that one? Oh, we did sine x equals a half. Maybe we did cosine x equals a half yesterday. So what would I have to do to get x by itself here? Sam?
You get the inverse cosine?
Yep. I'm going to take the inverse cosine of a half, and you get 60. And what other what other quadrant are we looking for an answer in besides 1?
Uh,
4. So what would be my answer in quadrant 4?
300.
360 minus your reference angle. So 300. Okay, it's a little bit different because it had the double angle identity. But once you use that, it factors and you can go from there. So pretty much every problem, I think, except one in the notes between yesterday and today, factored. Every problem today factored. So once you factor it, set each factor equal to 0 and use your ASTC chart, or visualize the graph in your head if it's a 0, 1, or negative 1. But that's every problem. Factor it, set it equal to 0. All right, so homework. I think I already gave you guys that yesterday. So it's 2 through 8, 13, 14, 16, 19, and 2 through 8 is just the evens. And this is the video from yesterday. So if I played this, I'd be recording a video with a video from yesterday. It's like a video in a video.
So why aren't you playing?
Well, I could, but then I'm at the end, so there's no more sound, I guess. Or maybe the sound is off. But it's a video in a video now. And then tomorrow I could bring it up again and it would be like triple video. It'd be like Inception or something. It's crazy.